Alrighty, well, I will begin. Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to help us to use this time wisely, just to prepare for the test, which is Thursday. And I just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so go over here. So is there anything you guys have questions about? One thing I wanted to look at before I forget is, because it just didn't happen in class this semester, I don't think. So like there's a problem on the bonus bonus quiz, and there's also a problem on the, whatchamacallit, the mission 2. So nothing especially exciting here, right? We factor, we got root -1 repeated here, and just one copy of root 1 from that, so I get the e to the x from the d minus 1, and these two guys from the d plus 1 squared. That's the general solution there. The next one was a complex repeated, so we've got a real part of 2 and an imaginary part of plus or minus 1, I. So that gives me the cosine, the sine, and then x cosine, x sine, and they're all multiplied by e to the 2x because of this d minus 2 squared term there. This quartic is a little bit more exciting. It factors like so, and you end up with a plus or minus root 3 and a plus or minus root 2, which gives you this general solution. And of course, you could also write that in terms of Cauchy-Cinch if you were so inclined, which is this Cauchy-Cinch thing is actually much to be preferred if we are using this solution in other contexts. So we should keep this in mind for our future purposes. But this one here is a little bit different, right? Because I put d to the 4th equal to d squared, and so that ended up giving me the characteristic equation lambda to the 4th equals to lambda squared, which if I rearrange and factor, I get 0 twice, minus 1 once, and 1 once for roots, which gives me this general solution, right? Then the thing I was actually getting this out to talk about is problem 5, see, because this is kind of a sneaky thing, which we haven't talked much about, but I should mention it. It is something I sometimes ask about. So here's the idea of this, is like, I've got this 5th order differential equation, right? Which, I don't know about you, but I'm not really that good at just like straight up factoring 5th order polynomials. Can you? I can't do it. However, if I have information, like the information that's given here is that e to the x and cosine 2x are both solutions. Well, if they're solutions, that means that there's a factor corresponding in the differential operator here, right? So like the e to the x means I've got a d minus 1 hidden somewhere in the L, right? And this cosine 2x, well, that means I've got a d squared plus 4, because that's where cosine 2x comes from. It comes from a d squared plus 4 factor. Yeah? So if I multiply these out, it gives me this lovely cubic. And so that's got to be a factor of L. And so to figure out what the cofactor to that is, well, I use long division. All right, so I take my 5th order and I divide in this cubic, and out pops this quadratic. If I did it right, I should get 0 here. Yeah, this one went okay. The one in the homework, I tricked myself into like, man, you got to be really careful. If you misplace the powers, you can, or you misplace powers, or also like forget to multiply. Like if there's a 2 here, and you don't multiply the 2 by the number here, that can get. I'll show you in a second here, but anyway, so if we did it right, we should get a remainder of 0. We do, and so what this all means. What does this all mean? This means that I can take this, right, times the divisor, which is that, and that gives me back L. That's what this long division means. And then, of course, we can unmultiply it, also known as factor it, like that, because, well, we knew where this came from, right? And in this case, nothing too interesting happens, because there's no like interplay between these factors at all, right? Like the 1, the 2, the 3 factors, they don't intermix really. There's just these 4 distinct factors, which ends up giving me these 5 fundamental solutions, right? Sine and cosine both coming from d squared plus 4, right? You can't have a cosine 2x in the solution without also having a sine 2x, right? At least in the general solution. let me just skip over to the corresponding problem in this, and then yeah, this one, problem 31, is kind of the same animal in your mission. And so like, when I was doing this, the first time I did it, like, when I got to the 2 times 9, I didn't multiply it, and it was bad. It was really bad. Like, everything just fell apart. But fortunately, I was able to white it out, and you can't even tell. If I didn't tell you right now, you might not be able to, I don't know. But anyway, so if we do it right, we should have remainder 0, as I do here. Now this one, I'm only given sine 3x as a solution, right? That gives me a d squared plus 9, so I can divide that. And since this one's just quartic, that's enough to get it down to a quadratic. Once we're at a quadratic, we can factor by completing the square or just by plain old factoring. And this one's a little bit more exciting. No, it's not. It's still boring. These guys don't really mix, I don't think. Yeah. So there's the solution. All right. So at this point, I'm going to stop talking and ask you guys if you got questions. What do you want me to talk about? Tell you what, let's look at the harder problems in here. I think you guys are probably okay with the earlier problems. Probably the ones that are more troublesome.
Can we go over the difference problems?
Then,
Towards the end, it should be like 40.
yeah, well, let's do these. Let's do problem 34, and then I'll go to whatever you're talking about. So problem 34 is useful because you're supposed to find the general solution to these problems. The reason I think this is useful is I do emphasize the annihilator method in here, right? But you don't misunderstand me. When I talk about the annihilator method, the reason I'm talking about that is to give you a tool to help you work yourself out of corners when you get to a hard problem, right? If the problem's not that hard, though, there's no need for the annihilator method. We can just write down the particular solution and solve it. All right? Like, in particular, if when we look at the homogeneous solution, there's no overlap, right? Because I've got e to the t, e to the minus 2t, e minus t. So I got a 1 and a t, right? There's no overlap here. So what that means is the naive solution, which is just formed from a linear combination of those kinds of things, you know, a plus bt, that's going to work. And so if I differentiate it once, then twice, and plug it back in, it just so happens you don't even need to do algebra here. You can just solve for yp is 11t minus 1. So there you go, we solved it. The general solution is going to be the homogeneous plus the particular, and that's what it is. So there's no need for annihilator method here, right? No need. The next one also, no need for the annihilator method because you've got, you know, sine 4x, cosine 4x for your homogeneous solutions, but your forcing term, it's got an e to the x times cosine 4x. So it's an entirely different function, right? And as such, and now this one's hard. It's a hard problem, right? You got to be good at differentiation. You got to be careful. Attention to detail matters here. You know, this is where having already taken calculus 1, 2, and 3 comes into play. You should be experts at differentiation now. And you get a chance to show your skills here, right? So you differentiate and differentiate and differentiate some more, and then organize terms. When you add them together, I end up getting these. And then we equate coefficients of like e to the x cosine and e to the x sine 4x. And I get these two equations and two unknowns, which we, of course, can solve. This one's easy to solve for b. And then I plug it into the other one. I get 1/65th for a and 8/65ths for b. And notice I didn't have to do the method of annihilators here because there's no overlap between the homogeneous solution and the forcing function. And how do I know I'm right here? I mean, I checked it with Wolfram Alpha personally. I just plugged it in, checked it, same answer, right? This one, again, no overlap. Sorry to be so boring, but you know, when I find the homogeneous solution, I have exponentials, but the forcing function's a polynomial. There's no overlap. So that means I can just, again, use particular solution at plus b, plug it in, work it out. There you go. Now, finally, part D, it gets interesting. See, because part D, when we look at the homogeneous solutions, we've got sine and cosine. But what's over here? cosine. Cosine's in the forcing function, right? So this is a problem where I probably should use the method of annihilators to make sure I set up my particular solution wisely. So what I do is I figure out what's the annihilator of the forcing function, namely d squared plus 1 and d minus 1 to kill off that and that, right? Then I annihilate the equation, and that gives me this homogeneous problem, which has this general solution. I look at that. I go, okay, well, this is the homogeneous part. That's not going to be part of the particular solution. I can basically just ignore that as far as the particular solution goes, and this is what I want for a particular solution. Since it gives me no joy to work in algebra C3, C4, and C5, I trade those out for A, B, and C. And I also factor out a T, as that will reduce the number of product rules I have to calculate by about half. Right, so this is just to make the algebra easier. I'm not done. This is the standard mistake you guys make, is like you feel like you've done something and it seemed like a little bit hard, you must be done with the problem. Not the case, right? Not the case. If you're finding the general solution here, you still have to plug it back in and find the values of A, B, and C, right? Do not deceive yourself into thinking you're done with a problem that's not done. On the flip side, if I say do not set up but do not determine the coefficients, do not determine the coefficients. Like, you need to follow instructions as to keep yourself from harm, right? Ignoring those instructions can make the test much more difficult than it actually is. So let's, anyway. All right, so this is my particular solution. I have to turn the page and plug it in. So I differentiate. First I differentiate, then I regroup terms to make it pretty. Then I differentiate a second time, and I regroup things to make it pretty. Then I write yp again, because then I figured if I add them, it's easier to add if I put them right next to each other, right? So kind of do a vertical stacking add on this problem. And so I got yp prime prime plus yp. And over here you can see stuff cancels, right? The TA minus TA, the TB, the minus TB. This is the secret sauce of the annihilator method working, is these terms canceling. And of course, we just left with that, which we can equate coefficients of cosine, sine, and exponential respectively to get a half for B, 0 for A, a half for C. And then we put it all together, and there's our solution. All right. The solution to a second order problem, the general solution, should involve two constants, not 4 or 5. Right? So there should not be undetermined coefficients in your, like, it's called method of undetermined coefficients, but that's a midway label, right? We actually do want to determine the undetermined coefficients for the solution. So what was your question about? Yeah, well, somebody had a question. I think it was you.
There was like a few questions on Newton's.
Oh, the application stuff?
Yeah.
Yeah, sure.
It was like 42, 43.
I think that sounds right. So 42 is harmless, right? Here you have mass 1, spring constant. This is a retarded spring problem. Mass 1, beta 4, spring constant K5. That gives me mx double dot plus beta x dot plus kx equals to 0. That's the setup here, right? And so I have, this is my characteristic equation. I complete the square. I read off the solution. I write down the answer, and yeah. Of course, if you wanted to, you could repackage this as a single amplitude times e to the minus 2t times the sine of a shifted sine. That's kind of nice for if you're like graphing it, this is nice because it's basically stuck inside this envelope of plus or minus a e to the minus t, right? So it's kind of like it's just, but anyway. Obviously you could tell from my wiggling exactly what the graph looked like, right? Because you're clairvoyant. But I'll try it. So these I was trying to here draw y equals a e to the minus t, and down here y equals minus a e to the minus t, right? If you've got a sign that's stuck between those two, what's it look like? It's wherever it starts, right? And then it just kind of oscillates. So that's what that solution looks like, right? It has to look like that because there's friction, so it should be the motion should be damped to 0 eventually, right? As energy is lost to the system and so forth. This was the RLC circuit problem. It's basically the same mathematics. This one's a little bit more annoying in the sense that it's got a non-homogeneous term. But so like, oh no, this is not the RLC circuits. My bad. That's just a label. This is still the spring mass problem with a force this time though. So we had mass 2, spring constant 32. It's actually not retarded because the beta is equal to 0 here. And so that gives you x double dot plus 16x equals to 34 e to the minus 2t cosine t, which is a problem we can solve. So notice that like the homogeneous solutions got sines and cosines for t, which means we don't need the method of annihilators because there's no overlap. So the particular solution just has the form, basically a derivative of this, which gives you an a cosine 4t and a b sine 4t times the exponential. You do some differentiation, you plug it in, out pops the answer. So after a page of algebra, yes. And then, of course, there is something to learn here in the sense that we get to so this is the general solution, right? But there's more here, right? Because we have initial conditions. So I have x of 0 is 0 and x prime of 0 is 0. So when I plug that into this stuff up here, it ends up giving me like c1 plus a half. See, that's coming from this. Where's the half coming from? What's cosine of 0? 1, right? So what's e to the 0? 1. So this just gives me a 1/2. That's this 1/2. And then when I differentiate this thing, I get a 4 cosine t from this piece. That's that 4c2. When I differentiate that, I get a, well, when you go through the derivative here, these are the pieces which remain. You might need to work this out on a side paper or something to see this exactly, because there's like a product rule you've got to do. You know, there's a bit of work here. But anyway, after the dust settles, we've got C1 is minus a half and C2 is minus 9/4. Then we put those back up in here, and that's the specific solution that solves this initial value problem. So this is important as a point of order. If I give you an initial value problem, you don't just use the homogeneous solution. If you've got a particular solution too, it's the particular plus the homogeneous which forms the actual solution to the problem. It's that you must fit the initial conditions to. All right, which is annoying because, you know, this might require some thinking in terms of like how that actually plays out for the derivative and so forth, but that is how it works. This problem is kind of interesting. So here we had x prime prime plus omega squared x equals to f naught cosine gamma t. To start out, we assume that gamma is not equal to omega, which means there's no overlap. So the particular solution looks like this. Twice differentiation gives you back minus gamma squared times the particular solution itself. So when you plug it in, you just have this. This is one of these cool problems where you can just solve for xp directly. And there it is. So that's the particular solution in this case. Now, so the general solution looks like this. Yeah. And that was part A. Then part B was like, hey, take the limit as gamma goes to omega. And so if I take the limit as gamma goes to omega of this business here, then what happens? I've got, it's an indeterminate type, right? Because this goes to like 0 over 0, right? So I use L'Hopital's rule, type 0 over 0. Differentiate this thing with respect to what? What am I differentiating with respect to? Not t, right? I don't differentiate with respect to t here. What's the variable? Gamma. Gamma is the variable. So I'm taking the derivative with respect to gamma, and when I do that, this piece, let's see here what happens. This piece drops out. We just get minus t f naught. Why is there a t there? Because the chain rule brings out the t. So I get minus t f naught sine gamma t over this minus 2 gamma, which then I've got, let's see here. Oh, then I can just, then it's not indeterminate anymore. I can just evaluate the expression and I get this is my solution, which is kind of neat, right? Because we're seeing that in the limit, as your forcing frequency goes to the resonant frequency, you're picking up that t times the sine function as your solution. So this is another way we can discover that in this case of pure residence, we have to multiply the particular solution by t, right? So there's about 7 different ways to derive why you have to multiply it by a t in the case that there's like a repeated root. This is one of the more, in my opinion, esoteric ways, but anyway, there it is. So the difference, of course, is significant. The difference is that in part A, the motion is, well, it's bounded, right? I mean, whatever this is, it's just oscillating back and forth. The spring might not break if it's not, if F naught's not too big. On the other hand, this solution, x gamma of t, it's got a t times the sign, right? As time goes to infinity, the spring is going to break, right? Like this is going to blow up. So that's that pure resonance that we saw from time to time. This is the actual RLC circuit problem. It's the same math again. I just have to put in the R and the L and the C into the defining differential equation. I get this equals 50, which gives me, I think, underdamped solution here, e to the minus t cos 3t, e to the minus t sine 3t. My particular solution looks like this because there's no overlap. And you plug it in, and our usual method out pops that. So this problem here, it looked scary, but it's actually really easy. All I was really asking you to do is to read the notes, find the critical frequency formula, and plug in the numbers. And when you do, you get a critical frequency of 6 for this one. And this one, the critical frequency formula works out to be -1, which means that actually in this case, we have to use the DC signal. The 0 frequency would give us the maximum amplitude. Logically speaking, the reason that's happening is we're optimizing this formula right here with respect to gamma being a non-negative frequency. So the domain in question is 0 to infinity, right? We can't have infinite frequency. So the only endpoint to check here really is 0. And so in this context, if there's no critical frequency for positive frequency, then 0 actually ends up giving us the maximum response. Whew. So you guys have questions? I actually have solved both the typo, both interpretations of the typo. Here's how it works out for x squared. And down here, here's how it works out for x cubed. So whatever you like, all right? But this is worth stopping and looking at for a second. So how would we have done this integral back in Calc 2? What would we have to do? Do you remember? How do you do integral of x cubed e to the x? Integration by parts, how many times? Yeah, 3 times, right? If there's an x cubed, your sentence is 3 integration by parts. And it's not that hard. But on the other hand, if I'm just solving dy dx equals to that, the homogeneous solution is just a constant, which means there's no overlap. So the particular solution is just an arbitrary thing of this form, which looks like that. And it's pretty easy to differentiate that one time and set it equal to what it has to be. And then you get these equations, you solve them, answer. I think that's faster than integration by parts 3 times, actually. You're like, well, I know the table method. Okay, fine. Whatever. But I think this is kind of interesting to go back and do these integrals in this way. You can disagree, but just something to think about. We have been solving differential equations ever since like the end of Calc 1. As soon as you got into integration, every integration is solving a differential equation, right? Because you're asking, what function can I differentiate and get back the integrand? That's always a differential equation of the form dy dx equals to the integrand. Let's see here. Let's go back to these. Not those. These are actually not, problem 41 wasn't too bad, actually. I thought it might be worse, but just a point of order. In part A, that's as far as I could get, so if that's as far as you got, that's fine. Like, I don't know how to integrate this either. So it's not something you've forgotten, it's just, that's what it is. That's the best we can do. And it's interesting, there's an asymmetry here, because when you go the other way, when you solve TS equal to 0, TSY equal to 0, then the story's different. I end up just being able to solve straight up for an explicit function of y, no integration, That's kind of cool, the asymmetry there. All right. I will post this, of course, guys. So, I mean, feel free to take pictures, but I'm planning to post it right after class. Right after I'm done teaching advanced, probably. I'm not sure I'll get to it between classes. I will try to post this between classes, guys. So these back here, these are the Cauchy-Euler problem. Do you guys have any questions about these? I mean, they're relatively straightforward. Basically, you just plug y equals x to the r into it, and every time you differentiate, it's basically power rule. Y prime prime gives us r times r minus 1. Y prime just gives me an r, and the 5 is just 5, right? This one, again, r times r minus 1 times 4 because of the y prime prime, and over here I just get plus 1. There's no differentiation, so it's just going to be 1. Right down here, 2, r times r minus 1 from that term, 3r from that, minus 1. And then besides that, we just have to solve the quadratic equation and interpret it properly. If we have a repeated root, we learned that we multiply by log x for these problems from the second linearly independent solution formula. And if it's a complex root, then we look at it in terms of this definition, which is that x to the I is actually a cosine log x plus I sine log x. Like generally speaking, if we have x to the, say, I beta, the way to do that is we think of it as e to the I beta natural log of x. So that's actually cosine of beta natural log of x plus I times the sine of beta natural log of x. So if we have a pure imaginary argument on x, it ends up giving us sines and cosines of logs. Yeah. Uh-oh. Yes. Yeah, that's exactly what happens. Yeah, yeah. Yeah, we just multiply by the log of x. If it was, like you said, if it was 1/2 three-peated, then the next thing would be plus c3 square root of x times the log of x squared. That's exactly what happens. Yeah. Let's see here. Oh yeah, this one I should stop and talk about for a second. If we don't have a formula for the inhomogeneous term, the best we can hope for is an integral solution, right? But variation of parameters allows us to set that up. So like this one, my homogeneous solutions end up being cosine of 3 log x and sine of 3 log x because of the Cauchy-Euler math. I calculate the Wronskian by y1, y2 prime minus y2, y1 prime. This is going to be the denominator in the variation of parameters formulas, right? And it simplifies to actually 3 over x. So that's pretty cool because you got a sine squared plus cosine squared here, right? And as such, when I calculate a times w, well, notice that here a is not 1. A is actually equal to x squared. So the variation of parameters is actually kind of interesting here. So my AW term, which is in the denominator of the variation of parameters formula, ends up being 3x, and that's why I have a 3x here. And here, this is minus y2g, and this is y1g. This is the v1 formula. This is the v2 formula. Make sure you have those on your card. Yeah.
What tells us again when exactly to use the Wronskian?
Well, what tells us to use the Wronskian? Well, I guess the question is, what's the question, right? So, going back to the start of this thing, one, and this is a very disingenuous answer to your question. How do you know to use the Wronskian? Well, sometimes I just ask you to calculate the Wronskian. So there's that, which is kind of not what you're asking about. But the other place where we use the Wronskian, so here is the actual Wronskian for that. But the other place would be variation of parameters. So if our non-homogeneous problem has a forcing function which is not a solution to to a constant coefficient problem, then we have to use variation of parameters. The denominator of the variation of parameters formulas is the Wronskian. And I would only ask you to do n equals to 2 variation of parameters. I'm not a monster. I wouldn't ask you n equals 3. That wasn't even your homework, so it's certainly not on the test, right? So I am showing you some trade secrets here. So here's some pro tips on how to make determinants easier. You can ignore these if you like, and you can just calculate by the column expansion if that's what you're comfortable with. By all means, just stick with that. But notice here, I can do a couple tricks. The one is, I've got e to the t everywhere, right? So if you've got e to the t like this, you can factor it out. And when you factor out a constant that's everywhere in the matrix, you end up pulling out the power of the constant to the size of the matrix. If it's a 3 by 3, I cube the constant. So that's why I bring out an e to the t cubed. Now if you think about the mechanics of how you calculate the determinant, this is not surprising, because in calculating the determinant, every term gets a exponential of t. And when you multiply those out, there's always 3 of them in every single term that forms the determinant, all 6 of them. So I could just pull it out at the start, saves me a bunch of writing. Then the other trick, and this is a mighty trick, is that you can do row operations. A row operation is like subtracting row 1 from row 2. So in row 2, I take row 2, the original row 2, and I subtract row 1. So t squared, I'm subtracting off the t squared, I subtract off the t. 1 minus 1 is 0, and the same for row 3. Again, I lose the t squared, I lose the t, I'm left with the 2 and the 0. Well, this is really nice, because then I can just expand on that number there rather than something else, and then I just have this, and so it just makes the calculation much, much easier if you happen to know those tricks. Now, you can still calculate it without knowing the tricks, obviously, right? Just problem 27 is kind of a, the purpose of problem 27 is the same as the purpose of the last problem in your homework, which is to try to open your mind to get you to think about principle of superposition. That if we can solve related non-homogeneous problems with the same defining differential operator, L, same homogeneous piece, then you can put together solutions from different forcing functions. Like physically speaking, what I'm saying is a linear system responds to each one of its, like if you have inputs to a linear system, it gives you a response for each input, right? And so you can understand the net response to a bunch of inputs as the sum of the responses to each input. This is the principle of superposition. That's what's behind the mathematics here as well. See, because we get x sine x for this, we get 1 plus x squared for that. So when I look at this, I'm like, oh, look at this. I've got actually 2 of these guys, right? And I've got minus 1 of those guys. So it means that twice y1 minus y2 will solve this. And like down here, I have 4 times the y2, and I've got output, and I've got minus 6 times the y1 output. So that stands to reason I can use 4 times the y2 minus 6 times the y1, and that will give me the desired outcome. Let me skip to the end of this. So last problem in your mission. This first one, this one's harmless. There's no overlap. You can plug it in, work it out. You won't feel like a lot of mental energy leaving your head. You'll get this. It won't be bad. That's the first part A. Part B was unpleasant. So part B is kind of nasty because there's overlap and it's hidden. It's wrapped away in the interworkings of the cosh, because cosh is e to the x plus e to the minus x divided by 2, which means that part of this, that part, is overlapping that, but not the other part, right? So I use the method of annihilators to set up the particular solution. It's everything in the middle is my particular solution here, which after some differentiation, like so, that got me to that, which then if you equate these like so, it gives you this equation, which at this point I ran out of time. Sorry. So anyway, here's a good check on my calculation. This plus that is canceling that. That's important because if it didn't cancel, I would not have an x squared e to the e to the x on the other side to balance it, which means that would force b to be 0, but b can't be 0, and this can, anyway. Long story short, this is what pops out. So And I've checked this a little bit. I'm pretty sure this is right. I mean, I'm almost certain this is right. I got this from Wolfram Alpha. But I do believe that this algebra implies that. So anyway, my setup does indicate exactly the solution type that Wolfram Alpha produces. So now, great. So part C. Part C, there was a typo. So I'm sorry about that. I wanted to put an X here so that A and B and C are related. All right? So if you tried this at all, you get full credit, right? So basically what's going on here is I've got twice the forcing function from A plus 10 times the forcing function from part B. So in other words, I know that if I put this as my particular solution, that'll pop out. And if I put that as my particular solution, x cosh will pop out. So all I have to do is take twice yp1 plus 10 times yp2, and then that will pop out. This is the principle of superposition. Now it's ugly. So that would be the solution here. I don't even have to do any further calculation. I can just use what I've already done to build the solution to part C. All right? So I oftentimes ask a question like this on the test, but not this ugly. All right? Like, I might be able to find one. Let's see if I can find one. Let me consult my archives here. Oops. That's the future. You guys like series, right? I know you're probably like a little disappointed in me at the moment because we haven't really done anything with power series yet in this class. And you're like, I worked really hard to learn power series, and you have not given me any opportunities to flex my power series muscles in here yet. It's okay, but I will make up for it as soon as we're done with test 1. So yeah, here. This is my my typical move. If you go back and you look at a bunch of my tests, you'll see I do this over and over again. So here's a problem: y prime prime plus y equals e to the t plus 2 sine t. This is a pain because the sine t's got an overlap. You got to multiply by t. This piece is not bad. You can do that easy. So out pops this solution. Great. What's the next problem? Y prime prime plus y equals to secant t. Ah, this is a variation of parameters. So we variation of parameters this thing, out pops this solution, yp2. What's the next problem? Solve, hint, without further calculation. Ooh, I was being nice this semester. Y prime prime plus y equals to e to the t plus 2 sine t plus 6 secant t. So what you got to do is just use what was just done up above and put it together, and there's the solution. This is superposition. So anyway, do you guys have other questions? We can go back and look at mission 1 if you want. It's up to you guys. We could look at this test if you'd prefer. I'll look at the test. All right. Let's see here. This test is kind of ballpark for you guys. So problem 1, that's a what? I mean, it's pretty easy to see what it is because the solution's in front of us, but hey, do you want me to, here, let's make this more mysterious. Give me a second. There we go. Ooh, now it's much harder. But seriously, no joke, this is a significant part of the difficulty of the test, is knowing which method to use, right? You need to figure that out for yourself. As a general rule of order, I try separation of variables first because that's the most natural, sort of obvious thing, yeah? And so this one you can solve with separation of variables. This one here, separation of variables isn't going to do it, but it's what? Integrating factor, yeah, because that's a linear differential equation. Notice that I only ask for the implicit solution, right? That means that you don't have to solve for y here. In contrast, I say find the explicit solution here, which means we do have to solve for y, right? Okay, we've got places to be. How about this? Find the implicit solution of 16x dx plus 9y dy equals to 0, which includes this point. What kind of differential equation is this? That one. This one should yell at you, exact equation, right? Of course, if it doesn't pop out at you, you could also do what here? You could separate and integrate also. So they're not mutually exclusive, but that's a... So let me go back to the solution here. I'm trying to go back to the solution. So we separate integral of secant squared. So a point of order, if you don't know the integral of secant squared is tangent, that adds a difficulty to this test that need not be there. But I've seen it happen. If I'm away from calculus 2 for a while and I come back to it, it happens to me too. But anyway, yeah. So then, on the other hand, what do I got? Oh, integral of tangent. That's a u substitution, like a u equals cosine substitution, which gives me that. So there you go. The integrating factor for the other one, it is so important to think about your integrating factor. You don't just do the integral and say, oh, I'm done. I'm going to multiply by this because that's helpful. No, it's not. You must simplify your integrating factor using correct algebra. In this case, 1 over x cubed. That is the helpful thing, because when I multiply this by 1 over x cubed, I can reverse product rule this and see that I have the derivative of the integrating factor times y. This must happen if we've done the calculation correctly. And so anyway, then we integrate both sides, and lo and behold, answer. The exact equation down here is pretty... So you're like, well, where did you come up with this? The answer is I just looked at it and wrote it down. I mean, we don't need to make it more complicated. I'm integrating the x part to get that. I'm integrating the y part to get that. I'm checking myself by taking the total differential of this expression, and out back pops the differential equation, so that's a good sign. Now, another point of order here. Well, this one I ask you to find the solution that goes through the point 3,4, right? So that means I have to choose a constant which makes that happen. That's easy enough to do. I just plug in 3, 4, and I find out my constant has to be 144, and there's my solution. A lot of times I don't give a specific point in this problem. I just ask you to find the general solution. It's very important to me that you don't just put a box around f, because f is not the answer. F equals to a constant is the answer. That is a solution set. The function f, while interesting as a level function, is not the answer. It is a step on the way to the answer. Right? So like if I just boxed this, if I just like box around f, answer, like no, you're not done. That's not the answer. Yes, you've got a cubic friction force with a K on it for some reason. I guess I got tired of beta. Find the velocity as a function of position s. Ooh, sneaky. Assuming that the particle undergoes one-dimensional motion with velocity v naught when s equal to 0. So in this case, ds dt is my v. So I change my dv dt to ds dt dv ds. I think it sounds more fun if we make it x, because then you get to say m dx dt dv dx, or v dv dx. See, v dv ds, it just doesn't have the same ring to it. But anyway, it's the same stupid trick. This is just the chain rule. And once I do that, I've eliminated time, right? And then we can separate and integrate, and yeah. In contrast, if I asked you to find the velocity as a function of time here, you just solve this equal to that directly, right? You'd have dv over v cubed equals to like minus k dt over m, and you could solve that just the same, right? It wouldn't be hard to find velocity as a function of position, but you have to mind the instructions, right? Problem 5 is a Bernoulli. As I told you guys, if I have one that requires a substitution, I will mention, hey, this requires a substitution. Unless it's the bonus question, I reserve the right to ask a bonus question which does not have the substitution advice. It's just a wild problem which you have to figure out. I may ask one of those. So obviously this becomes much easier if I tell you what it is and indicate that that's a good substitution to make. That's not right. Anyway, so some calculus. Some calculus happens, and then we plug in. So the substitution, just like U substitution, what did we hopefully drill into your head in the calculus sequences? When you make a U substitution, you must change both the integrand and what? The measure, right? The differential. You have to trade dx and du. Same thing here. You can't just change the differential equation part with the variables. You also have to change the dy dx. So both must come into play. That's an important aspect of these substitutions. I have to, figure out what dy dx is in terms of dw dx in this case. And when I do that, I get a linear problem, which then we can solve with the integrating factor method. Oh, look at this. I didn't use the integrating factor method. What did I do here? Do you see what I did? What did I do? I was like, hey, this is a constant coefficient problem. And I can just use the particular solution has the form ax plus b. There's no overlap, right? I can just differentiate that, plug it in, and out pops my answer. So just because it's linear doesn't mean you have to use integrating factor method, right? You could actually use our other methods if it's sufficiently simple like this, right? So anyway. And then, of course, you have to unsubstitute the substitution to get the answer. But well, that's boring. We just looked at this one already today. I guess I'm a creature of habit. But yeah, so there's that again. This one, repeated root, right? So we have to multiply, put the x here. Oops. What happened? My numbering is... Oh, never mind. I don't know how to scroll. Let's see here. General solution. So I got a factor d to the fourth minus 81, like so. I got 3. I got minus 3 for that one, 3 for that one, cosine and sine for that one. All right. Of course, this one you could also write with cosh 3x and sinh 3x if you wanted. Here's a setup, but do not explicitly find the undetermined coefficient's minimal particular solution. I keep forgetting to say this, guys, but I will try to put it on the test. I want you to give me the minimal particular solution. So I will take points off if you throw in things here that do not belong. In particular, the things students are most often likely to throw in that doesn't belong is they just keep the homogeneous part, right? Like the homogeneous part has got the c1 plus c2x plus c3 cosine x plus c4 sine x. I do not need these terms in the particular solution. Because if I put them in, what happens? They all dissolve. They always go to 0 when you plug it in. So this is the minimal particular solution, all right? Every particular solution I've found for you guys this semester has been a minimal particular solution, all right? That's always what I'm doing. So let's see here. So I have to find the annihilator for that, which is like what? I put it, what this d is, why is that d there? The d is there because that 3. 3 gives me the d. This is a lambda equals to minus 3 plus or minus 2i type term. So that corresponds to this quadratic factor, d plus 3 squared plus 4. Yeah, and then so I annihilate it, and then I write, that shows me that's the particular solution. And I think we already talked about this. Yeah. So, ooh. What's this? Suppose y1 is a solution of the differential equation m dx plus n dy equal to 0. If y2 is an orthogonal trajectory to y1, then what differential equation does y2 solve? Please leave your answer in Fathian form. So y2 has to be a solution to that, is the answer. Or if you like, n dx minus m dy equals 0, or that, etc. Of course, well, anyway. So we did talk, I haven't talked about this enough today. We've looked at a number of applications, right? We got the spring force, like the retarded spring stuff lately. We have springs with forces on them now. We have here's a force. Find the velocity as a function of time or a function of position. Ooh, what's this? Interesting. A third order linear differential equation defining. Show that. Interesting. This must have been my bonus problem. Yep, definitely. Okay. Of course, now that I've shown you it, I can't use it again. Probably. But where was I? So I was just going to go back and talk a second here about mission 1. So if you guys have done the missions, I really firmly believe this class is going to do significantly better than like last semester. Last semester I did not assign enough homework, and so when I gave a test, things just went haywire. So I think if you guys have done the homework, you have a good shot at my test being easy. This is what I'm hoping. I don't really have anything to say about these at the moment. I wanted to talk about so you guys remember the deal. We can check for exactness by taking the exterior derivative of the differential equation. Like if the exterior derivative of m dx plus n dy is equal to 0, that it tantamount to the closed condition holding, which is to say that m sub y is equal to n sub x. That's encoded within the exterior calculus, if you like. This is perhaps more important. You should definitely be able to find orthogonal trajectories to a curve or family of curves. That's a pretty common test question for me. I don't expect you to memorize or even know the polar trajectory thing. That was just for homework. That won't be on the test. All right. This is this thing, not on the test. That was a challenge problem for homework. Finding integral curve to a vector field very possibly could be on the test. Very much where I like the course to be. I think these problems are interesting. I would like you to know how to find the integral curve to a vector field. But of course, at the moment, I would only ask you to find the Cartesian form to the integral curve, because we don't know how to solve dx dt equals to p and dy dt equals to q just yet. That comes a little bit later, okay? So it's pretty simple. Like to find the integral curve, we just have to solve dy dx is equal to q over p, where q is the y component of the vector field and p is the x component of the vector field. So it's just another basically separation of variables problem typically. I think we've talked about the velocity, position versus time issue today. I do not expect you to know circuits and how to set up differential equations for circuits. I'm not a monster, despite the rumors. Yeah. I guess that's probably all I want to tell you. Do you guys have any questions or comments? Yeah.
Can you go through some of the Riccati questions?
The Riccati question. Oh, let's see, which one was that? Oh, this is what I forgot. I might ask you one of these if I'm not lazy to like plot solution curves, you know, but I'm pretty overwhelmed at the moment. Likelihood I can put this on the test is low, to be honest. Just put it on the test.
And make it 20 points.
Make it 20 points.
Please.
20 points to hand plot direction field noted.
Yes.
Don't agree to that. Don't agree to that. You don't want that.
Maybe 10 points.
No, you don't want to hand plot it. I changed the terms and conditions of what you asked for. Let's see here. So, where is that? Is that the next one? Where is the Riccati? Oh, okay. So, yeah. What about Mr. Riccati here? Did you have a particular question about it, or? Oh. Yeah, I don't really see the Riccati. I mean, if the Riccati equation is on the test, I have to like recite the whole preamble like in the mission. Like, I don't expect you to memorize the Riccati technique in that way. But essentially, it was just we have dy dx equals to some function. I see. I don't even remember it without looking back at the. I need to look back here. If we have some differential equation of this particular form, and if we have a known solution, then you can make a substitution that when you plug it in, the Riccati becomes a Bernoulli, and then you can solve it. So it's kind of wild. I mean, the Clairaut equation is even more wild in the sense that the differential equation has the form y is equal to xy prime plus some function of y prime, and look at that. Like this is the solution. You just write it down. Like, understand what's going on here for the Clairaut equation. We don't really have to like separate or integrate or anything. We just have a general solution type. We just write the solution down. And then like the singular solution, you have to solve these. But I mean, to be completely frank with you guys, it's not on the test, I don't think. Because we have many, many other irons in the fire for the test. It's only 75 minutes. But I think it's good for you guys to see these kinds of problems in homework. I think homework should be more expansive than the test, except, of course, for the evil bonus question that I will craft. But
Bernoulli will be on the test, though, right?
I didn't say that anything would be on the test specifically, but you could guess. See if I can find something. Oh, that's not it. My brother wrote a paper on partial fractions once upon a time.
A paper on partial fractions.
Yeah, like how general is partial fractions. When does it work? Why? Because he's a mathematician. That kind of thing, keeps him up at night.
Wait, what specifically was he trying to prove? Generalized method of undetermined coefficients.
So this is a paper I wrote with my brother. In this paper, we show that the method of undetermined coefficients generalizes for an arbitrary polynomial in a first-order operator. So, like, if you work at it, you can. Here, I'll just show you the problems we solve. So, if I can get to the problem we solve.
Your brother works at Appalachian State?
Yeah. So, for instance, if I was going to solve this differential equation, that one's not. Here's this Cauchy-Euler problem, like that. It's still not interesting. Here's a more interesting one. If I have the differential operator is 1 over 2t ddt, then it turns out that the analog, so like h is natural log of t for the Cauchy-Euler problem. H is t for the constant coefficient problem. Here, h is t squared. When I have a repeated root, I multiply by t squared for these guys. So if I have this differential equation s squared plus 25 cubed, if I have this one, s squared plus 25 cubed, it's got a root of plus or minus 5i